Hey, this is Sleeper, and welcome to the very first episode of Learn With Me. I'm going to be walking through the bug bounty hunter job role path on Hack the Box, and today we're going to start the first module, web requests. So we'll first start off with the module summary. So this module introduces key fundamentals that must be mastered to be successful in information security. Understanding web requests is essential for understanding how web applications work, which is necessary before attempting to attack or secure any web application. This makes this module the very first step in web application penetration testing. This module will deliver these concepts through two main tools, curl and the browser dev tools. These tools are among the essential tools in any web penetration tester's arsenal, and this module will start you on the path to mastering them. In addition to the above, this module will cover an overview of HTTP, the Hypertext Transfer Protocol, an overview of the Hypertext Transfer Protocol Secure, HTTPS, HTTP requests and responses and their headers, HTTP methods and response codes, common HTTP methods such as GET, POST, PUT, and DELETE, and interacting with APIs. A little more here. This module is broken down into sections with accompanying hands-on exercises to practice each of the tactics and techniques we cover. The module ends with a practical hands-on assessment to gauge your understanding of the various topic areas. You can start and stop the module at any time and pick up where you left off. There is no time limit or grading, but you must complete all the exercises and the skill assessment to receive the maximum number of cubes and have this module marked as complete in any of the paths you have chosen. As you work through the module, you will see example commands and command output for the various topics introduced. It is worth reproducing as many of these examples as possible to reinforce further the concepts presented in each section. You can do this with the poem box provided in the interactive sections or in your own virtual machine. This module is classified as fundamental and assumes a working knowledge of Linux command line and an understanding of information security fundamentals. Though not mandatory, we recommend taking these modules before/along with this module, Introduction to Networking and the Linux Fundamentals. So let's go ahead and start. Hypertext Transfer Protocol, HTTP. Today, the majority of the applications we use constantly interact with the internet, both web and mobile applications. Most internet communications are made with web requests through the HTTP protocol. HTTP is an application-level protocol used to access the World Wide Web resources. The term hypertext stands for text containing links to other resources and text that the readers can easily interpret. HTTP communication consists of a client and a server, where the client requests the server for a resource. The server processes the requests and returns the requested resource. The default port for HTTP communication is port 80, though this can be changed to any other port, depending on the web server configuration. The same requests are utilized when we use the internet to visit different websites. We enter a fully qualified domain name, FQDN, as a uniform resource locator, URL, to reach the desired website, like hackthebox.com. URL. Resources over HTTP are accessed via a URL, which offers many more specifications than simply specifying a website we want to visit. Let's take a look at the structure of URL. So here's what each component stands for. We have the scheme, examples HTTP colon backslash backslash HTTPS colon backslash backslash. Description here. This is used to identify the protocol being accessed by the client and ends with a colon and a double slash. The user info, example admin colon password at. This is an optional component that contains the credentials separated by a colon used to authenticate to the host and is separated from the host with an @ sign. The host, example inlanefreight.com. The host signifies the resource location. This can be a host name or an IP address. We have the port number, example 80. The port is separated from the host by a colon. If no port is specified, HTTP schemes default to port 80 and HTTPS default to port 443. We have the path, so example \dashboard.php. This points to the resource being accessed, which can be a file or a folder. If there's no path specified, the server returns the default index. Example index.html. We have the query string. Example $login equals true. The query string starts with a question mark and consists of a parameter, example login, and a value, example true. Multiple parameters can be separated by an ampersand. And lastly, fragments. For example, #status. Fragments are processed by the browsers on the client side to locate sections within the primary resource. Example is a header or section on the page. Now, not all components are required to access a resource. The main mandatory fields are the scheme and the host, without which the request would have no resource to request. So here is the HTTP flow. The diagram above presents the anatomy of an HTTP request at a very high level. The first time a user enters the URL, inlanefreight.com, into the browser, it sends a request to a DNS, domain name resolution server, to resolve the domain and get its IP. The DNS server looks up the IP address for inlanefreight.com and returns it. All domain names need to be resolved this way, as a server can't communicate without an IP address. Note, our browsers usually first look up records in the local etc hosts file, and if the requested domain does not exist within it, then they would contact other DNS servers. We can use the etc hosts to manually add records to is that a typo? records for DNS resolution by adding the IP followed by the domain. Once the browser gets the IP address linked to the domain, requested domain, it sends a GET request to the default HTTP port. For example, port 80, asking for the root/path. Then the web server receives the request and processes it. By default, servers are configured to return an index file when a request for / is received. In this case, the contents of index.html are read and returned by the web server as an HTTP response. The response also contains the status code, 200 OK, which indicates that the request was successfully processed. The web server then renders the index.html contents and presents it to the user. Note, this module is mainly focused on HTTP requests. For more on HTML and web applications, you may refer to the Introduction to Web Applications module, and that'll be after this. So here's the diagram one more time. The user requests the URL and obtains that from the server, translates it to IP. Okay, it's saying this is the IP, this is the URL, and good to go. Oh, first it goes up here. Okay, where is it? Here it is from the browser. Grab that IP and then sends back that for the user to view. Curl. In this module, we will be sending web requests through two of the most important tools for any web penetration tester, a web browser like Chrome or Firefox, and the curl command. So the curl, the client URL, is a command line tool and library that primarily supports HTTP along with many other protocols. This makes it a good candidate for scripts as well as automation, making it essential for sending various types of web requests from the command line, which is necessary for many types of web penetration tests. We can send a basic HTTP request to any URL by using it as an argument for curl, as follows. Nice. Sleeper at Hack the Box. So we curl inlanefright.com and it brings back in the HTML code that website. Let's grab some water real quick. Okay. We see that curl does not render the HTML/JavaScript/CSS code, unlike a web browser, but it prints it in its raw format. However, as penetration testers, we are mainly interested in the request and response context, which usually becomes much faster and more convenient than a web browser. We may also use curl to download a page or a file and output the content into a file using the -o flag. If we want to specify the output file name, we can use the -o flag and specify the name. Otherwise, we can use the -o, and curl will use the remote file name as follows. So let's curl inlanefright.com/index.html and list that. We have the index.html. As we can see, the output was not printed this time, but rather saved into index.html. We notice that curl still printed some status while processing the request. We can silent the status with the -s flag as follows. So curl -s-o, let's output the inlanefright.com/index.html. This time, curl did not print anything, as the output was saved into the index.html file. Finally, we may use the -h flag to see what other options we may use with curl. So curl -h, the help page for curl, to see what else is available. So we got -d data, the help, -i include, -o for the output, capital O remote name, write output to a file name as the remote file, silent to hide those status codes, -u for the username and password, capital -a for the user agent, so I guess you can specify that, and -v for verbose. As the above message mentions, we may use the -help all to print a more detailed help menu, or -help category, for example -http, to print the detailed help of a specific flag. If we ever need to read more detailed documentation, we can use the man curl to view the full curl manual page. In the upcoming sections, we will cover most of the above flags and see where we should use each of them. So let's start this instance. And we have a question. Answer the questions below to complete this section and earn cubes. Click here to spawn the target. To get the flag, start the above exercise, then use curl to download the file returned by /download .php in the server shown above. So we'll start that, and we have the target. So it's asking us to use curl to output the /download.php from the server. So this is the pwn box. We'll allow that, and we'll full screen this. So curl HTTP // Okay, let's go back and put a -o. We're just going to output this. Paste, and then /download.php, and just verify that looks good. We'll hit enter. Curl not specified. What did I do wrong? Maybe it's capital O. So lowercase o, you specify what it is. Capital O, it'll just take it as it is. So we'll want capital O. And we've got it. If we list, we can see that. And if we cat it, we can see our flag. So we'll go ahead and copy that and paste that in. So I'll edit this out after the fact. So mark complete and next. So yep, we're done there. Carrying on. So our second module of the web requests module, I guess second section of the first module. Hypertext Transfer Protocol Secure. In the previous section, we discussed how HTTP requests are sent and processed. However, one of the significant drawbacks of HTTP is that all the data is transferred in clear text. This means that anyone between the source and destination can perform a man-in-the-middle attack to view the transferred data. To counter this, the HTTPS protocol was created, in which all communications are transferred in an encrypted format. So even if a third party does not intercept the request, they would not be able to extract the data out of it. For this reason, HTTPS has become the mainstream scheme for websites on the internet, and HTTP is being phased out. And soon most web browsers will not allow visiting HTTP websites. So the HTTPS overview. If we examine an HTTP request, we can see the effect of not enforcing secure communications between a web browser and a web application. For example, the following is the content of an HTTP login request. We can see that the login credentials can be viewed in clear text. This would make it easy for someone on the same network, such as a public wireless network, to capture the request and use the credentials for malicious purposes. In contrast, when someone intercepts and analyzes traffic from an HTTPS request, they would see something like the following. As we can see, the data is transferred as a single encrypted stream, which makes it very difficult for anyone to capture information such as credentials or any other sensitive data. Websites that enforce HTTPS can be identified through the HTTPS : / in their URL. For example, google.com with that HTTPS right there, as well as the lock icon in the address bar of the web browser to the left of the URL. So if we visit a website that utilizes HTTPS like Google, all traffic would be encrypted. Excuse me. Note, although the data transferred through the HTTPS protocol may be encrypted, the request may still reveal the visited URL if it contacted a cleartext DNS server. For this reason, it is recommended to utilize encrypted DNS servers, for example, 8.8.8.8 or 1.1.1.1, or utilize a VPN service to ensure all traffic is properly encrypted. And here's the HTTPS flow. Let's look at how HTTPS operates at a high level. So here is the diagram, and we'll explain it down below. If we type HTTP instead of HTTPS to visit a website that enforces HTTPS, the web browser attempts to resolve the domain and redirects the user to the web server hosting the target website. A request is sent to port 80 first, which is the encrypted HTTP protocol. The server detects this and redirects the client to the secure HTTPS port 443 instead. This is done via the 301 moved permanently response code, which we will discuss in an upcoming section. Next, the client, the web browser, sends a client hello packet giving information about itself. After this, the server replies with the server hello, followed by a key exchange to exchange SSL certificates. The client verifies the key/certificate and sends one of its own. After this, an encrypted handshake is initiated to confirm whether the encryption and transfer are working correctly. Once the handshake completes successfully, normal HTTP communication is continued, which is encrypted after that. This is a very high-level overview of the key exchange, which is beyond this module scope. Note, depending on the circumstances, an attacker may be able to perform an HTTP downgrade attack, which downgrades HTTPS communication to HTTP, making the data transferred in clear text. This is done by setting up a man-in-the-middle attack, MITM, proxy, to transfer all traffic through the attacker's host without the user's knowledge. However, most modern browsers, servers, and web applications protect against this attack. So once again, here is the diagram. We request the website on the HTTP protocol. We're like, hey, let's get the port 80. They're like, no, you got to go to the secure website. We're like, okay, well, what's the secure website? We'll say hello. There's a key exchange. The server says hello. The client key exchange, encrypted handshake, we send that over, and we get the encrypted handshake back. Here is the website and the secure version. So curl for HTTPS. Curl should automatically handle all HTTPS communication standards and perform a secure handshake and then encrypt and decrypt data automatically. However, if we contact a website with an invalid SSL certificate or an outdated one, then curl by default would not be processed with the communication to protect against the earlier mentioned man-in-the-middle attacks. So we're curling the website on the HTTP S encryption, and it says invalid certificate chain. More details here. Modern web browsers would do the same, warning the user against visiting a website with an invalid SSL certificate. We may face such an issue when testing a local web application or with a web application hosted for practice purposes, as such web applications may not yet have implemented a valid SSL certificate. To skip the certificate check with curl, we can use the -K flag. So curl -K HTTPS / inlanefreight.com. It just brings us the normal website without this error. As we can see, the request went through this time, and we receive the response data. And continuing from there. So, HTTP requests and responses. HTTP communications mainly consist of an HTTP request and an HTTP response. An HTTP request is made by the client, for example, through curl or a browser, and is processed by the server, for example, a web server. The requests contain all of the details we require from the server, including the resource, for example, the URL, path, and parameters, any request data, headers, or options we specify, and many other options we will discuss throughout this module. Once the server requests the HTTP request, it processes it and responds by sending the HTTP response, which contains the response code, as discussed in a later section, and may contain the resource data if the requester has access to it. So here's the HTTP request. Let's start by examining the following example HTTP request. The image above shows an HTTP GET request to the URL. HTTP inlanefreight.com/users/login.html. So the first line of any HTTP request contains three main fields separated by spaces. I'll try to show both here. So the method GET, the HTTP method or verb, which specifies the type of action to perform. The path, so for example, /users/login.html. This is the path to the resource being accessed. This field can also be suffixed with a query string. For example, $username equals user. And then the version. Example, HTTP /1.1. The third and final field is used to denote the HTTP version. The next lines contain HTTP header value pairs like host, user agent, and cookie, and many other possible headers. These headers are used to specify various attributes of a request. The headers are terminated with a new line, which is necessary for the server to validate the request. Finally, a request may end with the request body and data. Note: HTTP version 1.x sends requests as clear text and uses a new line character to separate different fields and different requests. HTTP version 2.x, on the other hand, sends requests as binary data in a dictionary form. The HTTP response. Once the server processes our request, it sends its response. The following is an example HTTP response. The first line of an HTTP response contains two fields separated by spaces. The first being the HTTP version, example HTTP /1.1, and the second denotes the HTTP response code, example 200, OK. The response codes are used to determine the request's status, as will be discussed in a later section. After the first line, the response lists its headers similar to an HTTP request. Both request and response headers are discussed in the next section. Finally, the response may end up Finally, the response may end with a response body, which is separated by a new line after the headers. The response body is usually defined as HTML code. However, it can also respond with other code, such as other code types, such as JSON, website resources such as images, style sheets, or scripts, or even a document such as a PDF document hosted on the web server. So curl. In our earlier example with curl, we specified the URL and got the response body in return. However, curl also allows us to preview the full HTTP requests and the full HTTP response, which can become very handy when performing web penetration tests or writing exploits. To view the full HTTP request and response, we can simply add the -v verbose flag to our earlier commands, and it should print both the request and response. So curl inlinefreight.com -v, we send our request and then we receive our response. So get / and that's our version, and then in the response it's our version 401 error, unauthorized. As we can see, this time we get the full HTTP request and response. The request simply sent get /HTTP 1.1 along with the host, user, agent, and accept headers. In return, the HTTP response contained the HTTP version 1.141 unauthorized, which indicates that we do not have access over the requested source, as we will see in an upcoming section. Similar to the request, the response also contains several headers sent by the server, including date, content length, and content type. Finally, the response contained the response body in HTML, which is the same one we received earlier when using curl without the -v flag. Exercise. The -v flag shows an even more verbose output. Try to use this flag to see what extra request and response details get displayed with it. So it might ask us to do that down below, or we can do that in a minute. Browser dev tools. Most modern web browsers come with built-in developer tools, or otherwise known as dev tools, which are mainly intended for developers to test their web applications. However, as web penetration testers, these tools can be a vital asset in any web assessment we perform, as a browser and its dev tools are among the assets we are most likely to have in every web assessment exercise. In this module, we will also discuss how to utilize some of the basic browser dev tools to assess and monitor different types of web requests. Whenever we visit any website or access any web application, our browser sends multiple web requests and handles multiple HTTP responses to render the final view we see in the browser window. To open the browser dev tools in either Chrome or Firefox, we can click Control-Shift-I or simply click F12 on the keyboard. The dev tools contain multiple tabs, each of which has its own use. We will mostly be focusing on the Network tab in this module, as it is responsible for web requests. If we click on the Network tab and refresh the page, we should be able to see the list of requests sent by the page. As we can see, the dev tools shows us at a glance the response status. For example, the response code, the request method used, get, the requested resource, for example, the URL or domain, along with the requested path. Furthermore, we can use filter URLs to search for a specific request in case the website loads too many to go through. Exercise. Try clicking on any of the requests to view their details. You can then click on the Response tab to view the response body, and then click on the Raw button to view the unrendered source code of the response body. That's our flag from earlier. Okay. So we've got a couple questions here. So first, what is the HTTP method used while intercepting the request? So while intercepting the request, we'll see that in a moment. Let's just read both of these. And number 2, send a GET request to the above server and read the response headers to find the version of Apache running on the server, and then submit the answer and submit it as the answer. So answer format Okay. So we'll grab the IP and we'll close this out and we'll start it again here. Okay. So we'll just curl it. Let's do that triple V real quick. So we'll start it with just a V. We'll request it. Okay. So we also found the version number here, so we can just copy this and paste it in. It's Apache 2.4.41. And the HTTP method, I think it's just a GET request. Yeah, so we're requesting the website, so we're asking for it, we're getting the website. So this is the verbose version. This is the request, right? Let me zoom out a little bit. So our version, our response. Oh wait, this is our request. Get the web server or the IP and our response. Okay. And let's see what it looks like with a triple verbose. If there is any difference here that we can tell. Did it send? Oh, here we go. So HTML, does it show this? Looks about the same. I'm sure it'd be different if it was a more thorough website. So let's continue. So we got one more section in the HTTP fundamentals. HTTP headers. We have seen examples of HTTP requests and response headers in the previous section. Such HTTP headers pass information between the client and the server. Some headers are only used with either requests or responses, while some other general headers are common to both. Headers can have one or multiple values appended after the header name and separated by a colon. We can divide headers into the following categories. Number 1, general headers. 2, entity headers. 3, request headers. 4, response headers. And 5, security headers. Let's discuss each of these categories. So the general headers. General headers are used in both HTTP requests and responses. They are contextual and are used to describe the message rather than its contents. So we have the date, for example, the date, Wednesday, the 16th of February, 2022, 10:38 and 44 seconds GMT. It holds the date and time at which the message originated. It's preferred to convert the time to the standard UTC time. Let's see if that's the coordinated universal time. We have the connection. So connection close, for example, dictates if the current network connection, should stay alive after the request finishes. Two commonly used values for this header are close and keep alive. The close value from either the client or server means that they would like to terminate the connection, while the keep alive header indicates that the connection should remain open to receive more data and input. With entity headers, they are similar to general headers. Entity headers can be common to both the request and response. These headers are used to describe the content, the entity, transferred by a message. They are usually found in responses and post or put requests. So the content type, for example, content type text/HTML. It's used to describe the type of resource being transferred. The value is automatically added by the browsers on the client side and returned in the server response. The character set, or the char set, I guess. The char set field denotes the encoding standard, such as UTF-8. The media type application/PDF. The media type is similar to the content type and describes the data being transferred. This header can play a crucial role in making the server interpret our input. The char set field may also be used with this header. Boundary, for example, boundary equals string right here, acts as a marker to separate content when there is more than one in the same message. For example, within a form data, this boundary gets used as B4, E4, FBD 93540 to separate different parts of the form. We have the content length. Content length 385 holds the size of the entity being passed. This header is necessary as the server uses it to read data from the message body and is automatically generated by the browser and tools like curl. And content encoding, gzip. For example, data can undergo multiple transformations before being passed. For example, large amounts of data can be compressed to reduce the message size. The type of encoding being used should be specified using the content encoding header. Our request headers. The client sends request headers in an HTTP transaction. These headers are used in an HTTP request and do not relate to the content of the message. The following headers are commonly seen in HTTP requests. The host, for example, host inlanefreight.com, used to specify the host being queried for the resource. This can be a domain name or an IP address. HTTP servers can be configured to host different websites, which are revealed based on the host name. This makes the host header an important enumeration target, as it can indicate the existence of other hosts on the target server. The user agent, for example, curl 7.7 D7.0. The user agent header is used to describe the client requesting resources. This header can reveal a lot about the client, such as the browser, its version, and the operating system. Referrer, for example, HTTP inlanefreight.com, denotes where the current request is coming from. For example, clicking a link from Google search would clicking a link from Google search results would make HTTPS Google the referrer. Trusting this header can be dangerous, as it can be easily manipulated, leading to unintended consequences. Except, for example, *BAS /*. The accept header describes which media types the client can understand. It can contain multiple media types separated by commas. The *** value signifies that all media types are accepted. We have the cookie header. For example, PHP sesh ID equals that string. Contains cookie value pairs in the format name equals value. A cookie is a piece of data stored on the client side and on the server, which acts as an identifier. These are passed to the server per request, thus maintaining the client's access. Cookies can also serve other purposes, such as saving user preferences or session tracking. There can be multiple cookies in a single header, separated by a semicolon. And the authorization header. For example, basic, and here's our string. Another method for the server to identify clients. After successful authentication, the server returns a token unique to the client. Unlike cookies, tokens are stored only on the client side and retrieved by the server per request. There are multiple types of authentication types based on the web server and application type used. A complete list of request headers and their usage can be found here. We have the response headers. Response headers can be used in an HTTP response and do not relate to the content. Certain response headers such as age, location, and server, ASL, are used to provide more context about the response. The following headers are commonly seen in HTTP responses. So the server, the example Apache 2.2.14, Windows 32-bit, contains information about the HTTP server which processed the request. It can be used to gain information about the server, such as its version, and enumerate it further. The set cookie header, set cookie example PHP sesh ID equals this string here, contains the cookies needed for the client identification. Browsers parse the cookies and store them for future requests. This header follows the same format as the cookie request header. The www authenticate header, for example, basic realm equals localhost, notifies the client about the type of authentication required to access the requested resource. Security headers. Finally, we have security headers. With the increase in the variety of browsers and web-based attacks, defining certain headers that enhanced security was necessary. HTTP security headers are a class of response headers used to specify certain rules and policies to be followed by the browser while accessing the website. For example, the content security policy, script source self description dictates the website's policy towards externally injected resources. This could be JavaScript code as well as script resources. This header instructs the browser to accept resources only from certain trusted domains, hence preventing attacks such as cross-site scripting, XSS. The strict transport security header, the example here, max age with our digit here, prevents the browser from accessing the website over the plain text HTTP protocol and forces all communication to be carried over the HTTPS protocol. This prevents attackers from sniffing web traffic and accessing protected information such as passwords or other sensitive data. Refer policy header. Example origin dictates whether the browser should include the values specified via the referrer header or not. It can help in avoiding disclosing sensitive URLs and information while browsing the website. Note, this section only mentions a small subset of commonly seen HTTP headers. There are many other contextual headers that can be used in HTTP communications. It's also possible for applications to define custom headers based on their requirements. A complete list of standard HTTP headers can be found here. That was a mouthful. Curl. In the previous section, we saw how the -v flag with curl shows us the full details of the HTTP request and response. If we were only interested in seeing the response headers, then we can use the -I flag to send a head request and only display the response headers. Furthermore, we can use the lowercase I flag to display both the headers and the response body, for example, the HTML code. The difference between the two is that the capital I flag sends a head request, as we'll see in the next section, while the lowercase I sends any request we specify and prints the headers as well. The following command shows an example output of the I flag. So curl -I capital of our inlanefreight.com. We get the host, our headers, and that's it, our headers. Exercise. Try to go through all the headers above and see whether you can recall the usage for each of them. Probably not. There's a lot. The host, what we're trying to access. The user agent. This is the about the user, their browser, what they're using, cookie. This is kind of like the session authentication to keep their session active, accept maybe what kind of information is on the page. Refer, that was kind of the Google example. So we're taking it from this. This is our authorization, how we gained access to the page. And is this our response? Well, at least with the headers, this is the date. We're receiving more data, keeping the connection alive instead of closing it out. Exactly how much data is there, the content type, what is there, it's text. It was encoded. This is our server version number, Apache. We can review that above. In addition to viewing headers, curl also allows us to set request headers with the capital -H flag, as we will see in a later section. Some headers, like the user agent or cookie headers, have their own flags. For example, we can use a -A to set our user agent. For example, curl our HTTPS inlanefreight.com -A Mozilla /5.0. In the exercise, we could try to use the capital -I or the -V flags with the example above to ensure that we did change the user agent with the capital -A flag. And our browser dev tools. Finally, let's see how we can preview the HTTP headers using the browser dev tools. Just as we did in the previous section, we can go to the Network tab to view the different requests made by the page. We can click on any of the requests to view its details. In the first headers tab, we can see that both the HTTP request and HTTP response headers. The DevTools automatically arrange the headers into sections, but we can click on the raw button to view their details in their raw format. Furthermore, we can check the cookies tab to see any cookies used by the request, as discussed in an upcoming section. So here we go. The request and the response. There's our cookies. Okay, we can click up here to differentiate. Oh, I was like, what is this? Oh yeah, that's our pwn box from before. So another question. The server above loads the flag after the page is loaded. Use the Network tab in the browser DevTools to see what requests are made by the page and find the request to the flag. Okay, so it wants us to open it in our browser. And it also wants us to open the DevTools. I think that should be fine. Let's see if ftotal works. Okay. So it's asking to use the Network tab, and it's asking see what requests are made by the page and find the request to the flag. Okay, so is this, let's just view the page first. Recommended modules. So it's probably kind of hidden within this. So it was Control-Shift-I. We're on the network. I guess try to reload it. There we go. So this is kind of tiny, so I might try to load this in just my edge here. Okay, it does load. Let's go to DevTools, same thing, Control-Shift-I. Okay, so our network tab, let's view this. Let's refresh this again. Okay, here we go. And there's our flag. So this was on the network tab. Kind of went through some things, and the last thing here was our flag. So let's see. It's just part of the web page, kind of hidden in this directory. So we could curl that if we want. Let's do it. Back in our pwn box. Curl, paste, enter, list. Did it work? Oh, curl output, capital O. And we got it, we list it. That's our flag, but we can just copy and cat it. Can't see. Cat. There it is. Okay. And let's copy that and paste that in. Mark, complete, and next. So that's been the HTTP fundamentals section of our web requests module. Next time we'll be running through the HTTP methods and finishing up this module. So once again, my name is Sleeper, and that's a wrap. Until next time.